Alright, homework 4, video solutions. The very first problem has us using Euclid's algorithm to compute the greatest common divisor of two numbers. Recall that Euclid's algorithm, or at least the original version of Euclid's algorithm, developed by Euclid himself, takes advantage of this fact. The GCD of A and B, well, that's just the same as the GCD of B and A minus B. Why is that? Well, if something is a common factor of A and B, that is, if it divides A and it divides B, then it also divides A minus B. And conversely, if something divides B and A minus B, then it also divides A. So the common factors of A and B are the same as the common factors of B and A minus B, and therefore their greatest common factor is the same. Now, if we keep applying this rule to some pair of inputs, always subtracting the smaller one from the larger one to reduce it to a simpler pair of inputs over and over, we'll be able to reduce our pair of inputs down unthinkingly, uncleverly, algorithmically, until eventually we can apply this second rule. The GCD of something in 0 is just that something. And again, why is this? Well, to be a common factor of x and 0 just means you divide x and you divide 0. But everything divides 0. Anything times 0 is 0. So the greatest common factor of x and 0 is just the greatest factor of x, which is x. All the common factors of x and 0 divide x. Therefore, x is the greatest common factor of x and 0. So these two rules, just applied mechanically over and over, give us Euclid's original algorithm. But as we saw in class, we can actually speed it up. If we keep applying the first of these rules over and over, always changing the larger of our two input arguments by decrementing it by the smaller one, the result will be, over time, to have just applied this rule. The GCD of A and B is the same as the GCD of B and the remainder when A is divided by B. Right? If you keep subtracting the smaller input from the larger input over and over until you can no longer do so without going negative, well, you've basically taken the larger input and reduced it till the remainder when you can divide it by the smaller input. I may be phrasing that confusingly, but you've all seen this in class already. So now these two rules will be our optimized Euclid's algorithm. This is what I'll use to show how to compute the GCD of 527 and 323, although there's nothing wrong with the original subtraction-based version of Euclid's algorithm. All right, so let's see that in practice. So, the GCD of 527 and 323, this is the same as the GCD of 323 and 527 mod 323, which is 204. Right, 527 is 1 times 323 plus 204, so the remainder when you divide 527 by 323 is 204. All right, this in turn, again, applying our basic rule, which we'll apply over and over until we hit our base case with a 0, is the GCD of 204 and 323 mod 204, which is 119. 323 is 1 times 204 plus 119. So the remainder when you divide 323 by 204 is 119. So far, nothing's been happening that's not exactly how it would happen if we used the subtraction-based method. Instead, that's fine. This in turn is the GCD of 119 and 85. The remainder when you divide 204 by 119 is 85, because 204 is just 119 plus 85. This is the GCD of 85 and 34. 119 is 85 plus 34. Finally, we have our first step where we're going to do something that saves us time if we use mod rather than just subtracting. 85 mod 34, well, 85 is 2 times 34 plus 17. So 85 mod 34 is 17. It would have taken us 2 subtractions to reduce the argument 85 down to 17 if we just subtracted 34 each time, or we can get there in one step using mod. Great. Alright, so we have the GCD of 527 and 323 is the GCD of 323 and 204, which is the GCD of 204 and 119, which is the GCD of 119 and 85, which is the GCD of 85 and 34, which is the GCD of 34 and 17. Not quite done yet, but we're just about there. 34 mod 17 is 0. 34 is 2 times 17. And now we're done applying our mod rule. We can use our base case rule. One of the arguments here is 0. That means the GCD is the other one. Our GCD is 17. For all of these pairs, for the pair 527 and 323, for the pair 323 and 204, for the pair 204 and 119, and so on, all the way down to the pair 17 and 0, all of them have the exact same common factors. In all of them, the common factors are everything that divides 17. In all of them, the greatest common factor is 17. So now we have our GCD. All of these calls recursively, if you're computing this recursively, return 17. That's the answer to problem 1, part 1. So now, for part 2, we want to use the extended Euclidean algorithm. What is the extended Euclidean algorithm? Well, it's just the Euclidean algorithm with more bookkeeping, and the extra bookkeeping keeps track of how the final answer is some combination of the inputs. And by a combination, I mean something times the first input plus something times the second input. There's just this remarkable fact that the GCD of any two numbers can always be expressed in this way. And the reason this remarkable fact is true, well, there's a number of different ways you might see it, but one way of seeing it is just because we can do this extra bookkeeping. So let's see how that works. If I were to compute the GCD of 27 and 5, well, that GCD would be the same as the GCD of 5 and 2. Why is that? Because 2 is 27 mod 5. That's how our normal Euclidean algorithm works. But what does it mean to say that 2 is 27 mod 5? Well, it means 2 is 27 minus a multiple of 5. Excuse me. Sorry. 2 is 27 minus a multiple of 5. Specifically, 2 is 27 minus 5 5s. So I'm just going to write that down. We're going to want that later. Similarly, the GCD of 5 and 2 is the GCD of 2 and 5 mod 2. And 5 mod 2 is 1. Why is 5 mod 2 1? Because 1 is 5 minus a multiple of 2. In our case, 2 2s. The GCD of 2 and 1 is the GCD of 1 and 2 mod 1, which is 0, because 0 is 2 minus 2 1s. And finally, a 0 has popped up. We're at our base case. The GCD of 1 and 0 is 1. Alright, everything so far is just our normal Euclidean algorithm, except I've taken a little bit more care to note how each new argument is a combination of the previous ones. Now let's work backwards and see how our final answer is a combination of each pair of arguments along the line. At our base case, we say the final answer is always the argument that's not 0. So 1 is 1 times the argument that's not 0 plus, well, let's say 0 times the argument that is 0. 1 is 1 times 1 plus 0 times 0. Straightforward enough. Nothing interesting there. Now that we have it as a combination of 1 and 0, though, let's see how to express this GCD as a combination of 1 and 2. Well, the one part we're happy with, 1 times 1, but we don't want any zeros anymore, so let's express our 0, as we saw a second ago, as a combination of 1 and 2. It's 2 minus 2 1s. So we plug that in for our 0. Nothing very interesting happens here because it's all multiplied by 0, but if we plug that in, we get that 1 is 1 times 1 plus 0 times 2. Or let me write it in the other order. 0 times 2 plus 1 times 1. Alright, let's see a more interesting step. We know that it's 0 times 2 plus 1 times 1. Now let's express it as something times 5 plus something times 2. So the 0 times 2 part is good. This 1 times 1 part, not so great. We want to get rid of that 1 times 1. Turn it into something times 5 plus something times 2. Okay, well, we know how to express 1 as a combination of 5 and 2. 1 is 5 minus 2 2's. Okay, so we have 0 2's plus 1 times negative 2 2's. That gives us negative 2 2's total, on top of which we also have 1 5. So 1 times 5 minus 2 times 2. And that does indeed give us our answer of 1. So now we have 1 as a combination of 1 and 0, which we turned into a combination of 2 and 1, which we've turned into a combination of 5 and 2. Finally, for our last step, let's get it as a combination of 27 and 5. So we have 1 times 5, that part's great, plus negative 2 times 2, not so great, don't want that 2. Turn that 2 into a combination of 27s and 5s. 2 is 27 minus 5 5s. So we take 1 times 5 minus 2 times terribly sorry. They make me record these videos, sick or healthy. But 2 times 27 minus 5 5s, which gives us 1 5 plus negative 2 times negative 5 5s. So 1 5 plus 10 5s, that's 11 5s, on top of negative 2 27s. So we have negative 2 times 27 plus 11 times 5. And you can see that's negative 54 plus 55, which is 1. So now we know to express the GCD of 27 and 5 as a combination of 27 and 5. And we also know that that GCD is, in fact, 1. So probably on the homework they want you to write it something like this. Extended GCD or extended Euclidean algorithm. They'll probably say write it in this form. Instead of saying 1 times 1 plus 0 times 0 is the answer, they'll just want the coefficients in the answer. So maybe it looks like this. The GCD is 1, the first coefficient is 1, the second coefficient is 0. And similarly over here, coefficients were 0 and 1, but the GCD is still 1. And so on down the line. Coefficients were 1 and negative 2. Same GCD, of course. They're all going to have the same GCD. And finally over here at the top, the final answer we wanted, coefficients were negative 2 and 11. Same GCD of 1. I don't care how perfect my erasing is. Alright, whatever. Same idea as what I showed you before. They just might want you to write it in this format to match the format of the notes. Or maybe they don't, I don't know. But these are what all of these calls will return. Now what do we do with that? Well, we just saw that the GCD of 27 and 5 is 1, which is negative 2 times 27 plus 11 times 5. That's what this line right here means. So what? That's telling us that 1 is a multiple of 27 plus 11 times 5. In other words, it's 11 times 5. In the world of arithmetic, mod 27. If we get to ignore multiples of 27, if we get to pretend 27 is 0, then 11 times 5 is in fact equal to 1. So what? Well, by definition, that means 11 is the multiplicative inverse. Excuse me, inverse doesn't start with an O. Multiplicative inverse of 5 in mod 27 land. Oh god, I seem to have made my pen bolder. Well, it doesn't matter. So we just saw that 11 is the multiplicative inverse of 5 mod 27. Now let's use this to solve part 3. In part 3, we want to find out the value of x in mod 27 arithmetic if 5x plus 26 equals 3. Alright, well, what would we normally do to solve an equation like this in arithmetic, in an algebra class, say? Well, we'd subtract 26 from both sides. So 5x equals negative 23. But since we're in mod 27 land, that's the same as negative 23 plus 0, or negative 23 plus 27, which is 4. I'm only doing that to simplify it. Nothing wrong with saying negative 23, but 4 is a little bit simpler. So we see that 5x equals 4. The next thing we'd want to do is divide both sides by 5, or in other words, multiply both sides by the reciprocal of 5. Well, normally the reciprocal of 5, we'd just write 1/5. We could write that now too if we understood what we meant by it. What we mean by it is, in our case, 11, because 11 is the thing that, if you multiply it by 5, will give us 1 in our mod 27 land that we're working in. So if I take 11 and multiply it by both sides, I'll get 1 times x, 1 because 11 times 5, which is 55, is 1 mod 27. 55 is 2 times 27 plus 1, is equal to 11 times 4. That's 44, but we can simplify that. Mod 27, 44 is equal to 17. 44 is 27 plus 17. So we see that x equals 17. All the equations I've written here are, of course, mod 27. This whole thing, the whole time I'm working in mod 27 land. Even if I don't write it explicitly, I meant it implicitly. So that's the answer to part 3. X is 17. Finally, part 4. Finally, for problem 1. There's so much more of this video left. But finally, for part 4 of problem 1, we're asked, is it true or false that if a and b and c are integers and c is positive and a has no multiplicative inverse mod c, then ax equals b mod c has no solution? In other words, it's not possible for b to be a multiple of a mod c. Well, this is of course false. Even if a has no multiplicative inverse mod c, a does have a whole lot of multiples. There's a times 1, a times 2, a times 3. So if b happened to be a times 1 or a times 2 or a times 3, then there would be a solution. X would be 1 or 2 or 3. So I'm phrasing this very abstractly. If you just want to pick a random example to see that it's false, let's say a equals 2. Let's say c equals 6. A and c aren't relatively prime, their GCD isn't 1, so a doesn't have a multiplicative inverse in arithmetic mod c. But supposing we take b to be, I don't know, 4, there is in fact a solution to ax equals b mod c, since it's just the equation 2x equals 4 mod 6, and whether it's mod 6 or not, this equation has the solution x equals 2. So, false. It's not always the case that something like this has no solution. In fact, if you cared to be more specific, which you don't have to be for this homework, just say false and give an example like that. But if you cared to be more specific, what you could say is that it turns out ax equals b mod c has a solution just in case b is a multiple of the GCD of A and C. Why is that? Well, we know that the GCD of A and C will be expressible as some multiple of A in mod C land, because there's some way to say A times X plus C times something equals GCD of A and C by our extended Euclidean algorithm. The GCD is some multiple of A plus some multiple of C. And therefore, AX equals GCD of AC has a solution in mod C land. And by multiplying that particular value of X through by whatever necessary factor, you can solve AX equals B in mod C land for any value B, which is a multiple of the GCD of A and C. And conversely, if AX equals B mod C, then it must be the case that AX plus something times C equals B. Well, the left-hand side here is divisible by the GCD of A and C, and therefore the right-hand side would also have to be divisible by the GCD of A and C. So, using this vertical line to mean divisibility, the GCD of A and C divides the left-hand side, therefore the GCD of A and C would have to divide the right-hand side of B. So we've seen that there is some X such that, no, that's a very large dot, but there is some X such that AX equals B mod C, just in case B is a multiple of the GCD of A and C. But like I said, you don't need to say any of that for this problem. Just need to say false and show a counterexample.